Okay, so I'm trying to track climate solutions in a couple of places. One under coming attractions in a course called Drawdown, and the other one here under climate science, climate change, climate modeling, in which I have a section on modern climate change, where I have some net zero podcasts, and I'm going to add something called new findings, where I'm going to keep adding whatever I think look kind of exotic or promising in terms of climate solutions. This one is a Nature paper about how we could separate urine in wastewater and produce significant amount of fertilizers out of it, while also reducing contamination of coastal waters, groundwaters, and soil, and so on and so forth. Okay, so I'll start with this figure, which is from Will Stephen's paper here in Science, called the planetary boundaries. The concept evolved with Rockstrom, and they keep updating this figure over time. The quick criticism, of course, is that this is a good way to track, maybe define safe operating spaces for a few things under climate change, like what new things may emerge, like we have CFCs, HFCs, ozone hole, which is separately mentioned here, stratospheric ozone depletion, atmospheric aerosol loading. We don't know where we are or where the safe operating space is. Ocean acidification, we are still there's a chopper going by. So ocean acidification, we are still okay. Genetic diversity, we have kind of exceeded the boundary according to these metrics here. So you have a safe operating space here. We are below the boundary, planetary boundary. Planetary boundaries are not yet quantified for some of these things like functional diversity, for example. In the zone of uncertainty, but risks are increasing, and in the reddish colors we are beyond the zone of uncertainty, and we have already crossed the safe operating space with high risk already in place. Okay, so the urine story relates obviously to nitrogen. Since the Haber-Bosch process in the early 1900s, especially after industrial scale production of fertilizers, the use of fertilizers for agriculture has obviously been very beneficial in terms of the green revolution, increasing food production, reducing starvation, and so on. But it has also resulted in us crossing the safe operating boundary for nitrogen, but also for phosphorus. So the idea of this paper that I want to discuss here in more detail is about separating urine. So you can see this toilet design that is suggested when people pee. It can be piped away separately to let it to prevent it from getting into the common pool of wastewater. So the key to recovering nutrients from urine is to separate it from the rest of the waste system. A process called urine diversion. So UT systems range from those that process urine and feces on the spot to those that connect to larger sewage systems. In urine trap design by the Austrian firm EUS, urine runs down the front of the bowl and over a lip into a separate pipe. Such concepts are also used in composting toilets, where the idea is to convert human feces into soil over time by letting them separately get rid of all the smell and the other things that eventually it naturally becomes a soil. I won't go into the details, but there also urine has to be separated because adding water to the feces always creates problems and delays the transition to soil and so on. So this is just a schematic of how there is the toilet bowl, and here is nice vegetation that is growing as a Obviously this image is a little bit bizarre, but you can think of it as looking at it from the top into the toilet bowl here. Okay, so what are the numbers we are looking at? Nitrogen demand. The amount of nitrogen fertilizer used in agriculture has climbed to more than 8 times what it was 60 years ago. Much of it is produced using an energy-intensive process that relies on fossil fuels. So ammonium, industrial scale productions of ammonium for fertilizer is very energy intensive, and here are the various big demands coming from. China, India of course dominate, so Asia is huge here, with Europe and the Americas down here, and Oceania adds a little bit, and Africa is adding a little bit more. But from 1961, with under 100 million tons, by 2019 we have crossed over 100 million tons of nitrogen per year being used. What's in urine? A study of urban waste water globally suggests it holds enough nitrogen, phosphorus and potassium to offset more than 13% of the agricultural fertilizer demand. The value of those recovered nutrients would equal US 13.6 billion annually. So here is the potential revenue per year, US dollar billion, for potassium, phosphorus and nitrogen. Global fertilizer demand here in terms of percentage for potassium, phosphorus and nitrogen. Nutrients in wastewater in teragrams, 6.3 in terms of phosphorus, 3 for potassium, 3 for phosphorus and 16.6 teragrams for nitrogen. And there are already also lots of stories about how mining for potassium is creating lots of land use problems and other externalities like water contamination, water quality losses, conflicts and so on and so forth. Obviously when you do this, the energy used to accomplish this goal of separating urine and extracting nutrients out of it have to be considered, and the economic outcome or the market value of these nitrogen and phosphorus and potassium extracted from urine is a good number, but it has to also make sure that it is consistent with the net zero and carbon neutral kind of goals, which are not always very explicit unless you do life cycle analysis kind of evaluations from end to end. So here is a little bit more detail. From P to products, researchers are exploring various ways to make urine into something valuable, such as fertilizers. So here are some examples. In rural areas, especially in low-income regions, farmers can age urine in containers to kill off pathogens and then apply to fields, which is similar to composting feces, human shit into fertilizer. So here's a storage tank. In this case it's easier to separately drive urine into a tank and store it, or some urine diversion toilets could connect to new types of system that extract valuable components of urine so that they can easily be collected and transported to facilities and turned into products. So you need separate process, so on-site processing and storage, collection, vehicle, transportation, farms, factories and other facilities. Thirdly, self-contained urine diversion toilets that dry urine could be installed in bathrooms without adding pipes. So this would be just retrofitting existing systems and then wastewater and urine separately transported after drying, for example. Finally, here in new or renovated residential buildings or offices, a separate network of pipes could carry urine to the basement where a system could process and concentrate it for collection. So that's different than drying at individual toilet level. Okay, so various options available. People were asked if they would consume food fertilized by urine, but there was a wide range of acceptance. So you can see the global average of acceptance is at 59%, but the various countries, Bangladesh is low, Brazil, China are high, France is very high, India is also low, similar to Bangladesh, similar cultural practices and cultural values about human waste, which is a big problem in composting toilets as well. Jordan is low, without getting into any religious connotations. United States is high, Uganda is very high, and so on. So on average, in fact, in countries like India, there is a lot of illegal use of wastewater for irrigation of certain leafy vegetables. Contamination by E. coli from those can be very high as well, but obviously legitimizing the wastewater conversion to irrigation water or other uses is much more, because people are aware that it is being done and they are making a choice similar to the urine irrigation we are talking about here. But there are caveats about using recycled or retrieved wastewaters for such uses. Okay. Future pollution, the amount of nitrogen and phosphorus pollution that goes into surface waters climbs rapidly in a modeling study that explores future scenarios called shared socioeconomic pathways, which we talked about. So the CMIP-5 released in 2014 used representative concentration pathways, but shared socioeconomic pathways were developed, and CMIP-6 that is now being released is using SSPs. SSP scenarios go through things like this. So slow green shift, middle of the road, fragmented world, inequality gaps widen, innovation and sustainability. So projections to 2050, various scenarios offer various levels of teragrams of nitrogen addition to the system, and similarly for phosphorus, just note the numbers are much lower for phosphorus in teragrams. As for human sewage, a modeling study suggests wastewater adds 6.2 million tons of nitrogen to coastal waters around the globe. Nitrogen to coastal waters changes the nitrogen to phosphorus ratios and species compositions, and then they have other additional impacts on nutrient cycling, carbon sequestration, productivity, fisheries, livelihoods, and so on and so forth. Okay. Sources of wastewater nitrogen that enters coastal waters: no or very poor toilet facilities, septic tanks, and sewers with treatment. China dominates here with sewers with treatment contributing a lot. So that is in million tons. So 1890 for China. India is second. US obviously has much higher fraction of sewers with treatment. Brazil, you can see developing countries has higher fraction of no toilet facilities or very poor toilet facilities and septic tanks as well, and so on down here. Indonesia, Bangladesh, Germany, and so on and so forth. Obviously relates to population levels as well. Long story short, climate solutions will have to consider all possible options, not only for retrieving and recycling, reusing, but also reducing waste, and with population projections and so on. We also have to look at innovative solutions like this, where separating urine and extracting nitrogen and phosphorus and potassium, and reducing the industrial production of the same things or mining them for fertilizer use, to add to the overall lowering of our impacts on the environment. Okay.